Deep beneath our feet, an invisible force field surrounds our planet, a silent guardian that has protected life for eons. This is Earth's magnetic field, a vast, dynamic shield stretching thousands of kilometers into space. It deflects harmful solar winds and cosmic rays, making our world a habitable oasis in the vastness of the cosmos. But this shield isn't perfect. It has a weak spot, a growing and moving anomaly that has puzzled scientists and intrigued space agencies for decades. This is the story of the South Atlantic Anomaly, a mysterious dent in our planet's magnetic armor. Imagine Earth as a giant bar magnet with a north and a south pole. Lines of magnetic force arc out from the south and loop back in at the north, creating a protective bubble called the magnetosphere. This field is generated by the movement of molten iron in our planet's outer core, a process known as the geodynamo. It's a complex, ever-churning engine that's been running for billions of years. However, the geodynamo isn't perfectly symmetrical. The flow of molten metal is chaotic and turbulent, causing the magnetic field to have bumps, dips, and irregularities. One of the most significant of these irregularities lies over the South Atlantic Ocean, stretching from the coast of South America to the southern tip of Africa. Here, the magnetic field is significantly weaker than anywhere else on Earth. This region is the South Atlantic Anomaly, or the S. Within this area, the inner Van Allen radiation belt, a band of highly energetic charged particles trapped by Earth's magnetism, dips closer to the planet's surface than usual. Normally, this belt is held at a safe altitude, but in the SAA it descends to within just 200 kilometers of the ground, well into the orbit of many satellites. So, what does this magnetic weak spot actually mean for us down here on the surface? The good news is, for life on Earth, the South Atlantic Anomaly poses no direct threat. Our thick atmosphere provides more than enough protection from the increased radiation that sneaks through this magnetic dent. You won't feel any different flying over it. And life in South America and Southern Africa carries on completely unaffected. The real drama unfolds hundreds of kilometers above our heads, in the silent realm of low Earth orbit. For satellites and spacecraft, the SAA is like a treacherous cosmic pothole. When a satellite passes through this region, it is bombarded by a high-energy proton storm. These energetic particles can wreak havoc on sensitive electronics. They can cause glitches in computer memory, leading to data corruption or temporary shutdowns. In more severe cases, they can cause permanent damage to a satellite's systems, effectively shortening its operational lifespan. Think of it like flying a delicate drone through a hailstorm. The risk of something going wrong increases dramatically. Space agencies like NASA and the European Space Agency (ESA) are acutely aware of the dangers. The Hubble Space Telescope, for instance, powers down its sensitive scientific instruments whenever its orbit takes it through the anomaly to avoid damage. Astronauts on the International Space Station have reported seeing bright flashes of light even with their eyes closed as cosmic rays pass through their retinas, a phenomenon known as cosmic ray visual phenomena, which is much more frequent when the station is in the SA. To protect the crew and the station itself, extra shielding is installed in sleeping quarters and critical areas. It's a constant game of avoidance and mitigation for anything we send into low Earth orbit. What's causing this anomaly? Scientists believe the answer lies deep within the Earth's core. The SAA is thought to be linked to a feature at the core mantle boundary, a vast region of dense rock about 2,900 kilometers beneath our feet. Specifically, a large, dense structure known as the African Large Low Velocity Province seems to be influencing the flow of molten iron beneath it. This disturbance in the geodynamo creates a patch of reversed flux on the core's surface, an area where the magnetic field is oriented in the opposite direction to the main field. This patch of reversed magnetism is what creates the weak spot we observe at the surface. It's a bit like having a small magnet taped backwards onto a giant planetary magnet, creating a localized disruption. One of the most fascinating aspects of the South Atlantic Anomaly is that it's not static. Data collected over decades shows that it is drifting westward at a rate of about 20 kilometers per year. Even more intriguingly, it seems to be growing and deepening. Recent studies from ESA's Swarm satellite constellation, which precisely maps Earth's magnetic field, have revealed that the anomaly might be splitting into two distinct lobes, or minimums, one over southwestern Africa and another over the eastern Pacific. This evolution has led to some captivating theories. Some scientists speculate that the growing SAA could be a sign of something much bigger on the horizon, a complete reversal of Earth's magnetic poles. This event, known as a geomagnetic reversal, is when the magnetic north and south poles swap places. Fossil records show this has happened hundreds of times in Earth's history, roughly every few 100,000 years. The last full reversal occurred about 780,000 years ago, so some might say we are overdue. During a reversal, the main dipole field weakens significantly, and multiple smaller north and south poles could pop up all over the globe before the new orientation finally settles. In this scenario, the South Atlantic Anomaly could be seen as an early symptom of this planetary scale change. The process isn't instantaneous. It could take thousands of years to complete. During this transition, the planet's magnetic shield would be much weaker overall, not just in one spot, potentially exposing the entire globe to higher levels of solar and cosmic radiation. However, it's important to maintain perspective. While a full pole reversal is a dramatic idea, it's not a doomsday event. Life has flourished through countless reversals in the past. Our technological society, however, would face significant challenges. Power grids, communication systems, and of course, our entire satellite infrastructure would be extremely vulnerable. That's why understanding the behavior of the South Atlantic anomaly is so crucial. It's our best real-time laboratory for studying the complex dynamics of Earth's deep interior and the behavior of our magnetic field under stress. Scientists continue to monitor the SAA with an array of instruments, from ground-based magnetic observatories to sophisticated satellite missions like SWARM. By combining data from different sources, they build complex computer models that attempt to simulate the geodynamo and forecast the future evolution of the magnetic field. Each new piece of data helps refine these models, giving us a clearer picture of the forces at play deep within our planet. It's a detective story on a planetary scale, with clues buried thousands of kilometers beneath our feet and consequences reaching far out into space. The South Atlantic anomaly is a beautiful reminder that our planet is not a static, unchanging rock. It is a living, breathing system, full of complex and powerful processes that we are only just beginning to understand. It's a place of scientific mystery that connects the deepest parts of our world with our ambitions in space. While it presents a challenge for our technology, it also offers a unique window into the heart of our planet, revealing the secrets of the invisible shield that makes our existence possible. As we continue to watch this magnetic weak spot drift and evolve, we learn more not just about the risks it poses, but about the fundamental nature of our dynamic and ever-changing home. Thank you for joining me on this journey into one of Earth's most intriguing mysteries. If you found this exploration of the South Atlantic anomaly interesting, please consider liking this video and subscribing for more deep dives into the wonders of our world. Until next time, stay curious.